the reaction of creating a bubble in a atmosphere is to cause gas to move to the bottom of the bubble and then squirt up like a drop of water hits a lake. There's a squirt of thermal gas that goes right up along the same place where the jet wants to move. So these jets have very low momentum, and when they encounter material that moves along the same region that they're moving, they get deflected, so that you see not just two hotspots. In this case, there are actually four, but you get many of these sources have multiple hotspots, and I believe it's just due to the deflection of the low momentum jets, relativistic jets, by this thermal material that's in the same pathway. Okay, this is the radio picture, first discovered in the 30s. This is a classical double radio source at 5 gigahertz, and you see two separate lobes, and it's about 10 to the 7 years old, based on just the lifetime of the synchrotron electrons. But the whole region inside here is filled with radio radiation. This is an important point. So what we're seeing here is not just the 5 gigahertz, but the lower, as you go further from the hotspot region toward the central galaxy, the electrons are getting older and they radiate at lower frequencies. So you get a whole beautiful monotonically varying at mean radio frequency with radius. This is very common. Also notice that the front end of these radio lobes is not just a point. In my 2D calculation, I do not include these deflections of the jet, only one jet. So my calculations show a front end that's has a much sharper boat-like shape. Whereas here you can see that there's these rounded contours here are due to the fact that the jet is just moving around. The current jet hasn't even made a hot spot yet. Here it is. Very small and faint and very difficult to observe. Here are some theoretical models, and it's a mess. These are the most recent I could find in the literature. These are done by shooting jets out from the middle in both directions, and you get what amounts to a Kelvin-Helmholtz instability here as material flows back toward the central galaxy coming from the hotspot region. And the sources don't look like this. The radio emission does not look like this or this. It looks like the Cygnus A is typical. It has kind of a nice rounded contour. So there's clearly a need for more computations. And what I did here was to do 2D asymmetric, axisymmetric computations with all the standard MHD's equations, except I include now the energy density of the cosmic rays. I'm ignoring the diffusion of cosmic rays. So this is like a second fluid. So there are two fluids here. There's the gas, thermal energy density of the gas, and then there's the cosmic ray energy density, which is relativistic. The other thing that I consider is the time element. The age at every grid point in the radio cavity, I can calculate the time that the material there left the shocked region. And this is very useful for calculating ages of the cosmic rays. So I add vector quantity, which is the density in the shock spot, called just behind the jet shock, and the local time, the cosmic time when that material was in the shock spot. And then later I can calculate at any point inside the radio cavity the age of the particles at in that grid zone. The polarization observations tell you the orientation of the magnetic field. Generally what you see in the hotspot regions is a field that is perpendicular to the jet. This is just because there's a 1D compression. Any field configuration, if you flatten it in 1D, would look like this. It does look like a toroidal field, but it need not. It's more complicated. Certainly as this material flows back into the radio halo, this is not a purely toroidal field. So what I'm assuming here is that I'm going to ignore the jet entirely and start the calculation with a moving shock spot consisting of several zones that moves zone by zone out along the z-axis. And that's okay, because the jet, we don't understand the jet, but the hotspots are well observed. We know the particle distribution, a lot of physics about them. And in this region, which I call the shock spot, I add 10 to the 46 ergs per second. That number is just an order of magnitude. And it roughly matches the volume that we see in Cygnus A today. And I also add 1 solar mass of non-relativistic gas each year to give the magnetic field something to freeze into. And I'm assuming a toroidal hotspot field. I'll talk more about that in a moment. And I reset, after each time step, I reset that field to some constant value. So everything, field, cosmic rays, and gas inside the radio cavity all come from the shock spot. The shock spot velocity is not very fast, 6,000 kilometers a second. That's just the size of Cygnus A divided by its age. So the model I have is a virtual jet, which is not computed, and zones that move zone-wise, step by step, at this velocity along the z-axis out into the cluster gas. And this stuff is very hot here. It expands it at some decent fraction of the speed of light. And I also assume that none of this stuff goes upstream into the oncoming jet. Now, the assumption of a toroidal field is nice and convenient because it automatically satisfies div B equals 0. It satisfies the induction equation. The poloidal fields, if you want to include BR and BZ, cannot be used with ordinary MHD codes like Flash and others that people use. And the reason for that is that I'm putting in a source function. All these codes use something called constrained transport, which means that if div B is 0 at the beginning, the code is guaranteed to preserve that to machine accuracy later in the calculation. But I'm not doing that. After each time step, I'm resetting the B field in the shock spot to some value, like 100 microgauss or something like that. And what this does when I reset is break the lines of force. That creates magnetic monopoles around the shock spot, and they don't go away. They stay in the calculation, and if you just did this with Flash, you'd think you were getting some result that looked reasonable, but in fact it could be really quite wrong. So what I'm doing is putting in a large-scale toroidal field to get some sense about what happens. And toroidal field is nice because it has this div B equals 0 guaranteed. Well, what you find is that there is this Kelvin-Helmholtz instability. What these guys were doing in those images is correct, and I'm getting it too. As material flows back, this is a velocity map. These arrows are so close you can't see the arrows, but it comes out of the shock spot and flows back along the outer edge of the radio cavity and becomes Kelvin-Helmholtz unstable at the inner surface, not the outer surface. The sense of the curvature is in. If it was at the outer surface, this would curve out. In other words, the first instance of KH instability is an inward motion, which means that it's the physics inside the cavity is what determines this in my solution. So there's a boundary backflow, is the term I'm going to use, of material that comes from the shock spot. And using that equation I showed you, you can calculate the projected mean age of the cosmic rays. And here, a close analysis of this shows that it's not monotonic, because you're mixing this stuff up inside the radio cavity. The ages are not monotonic. They're being scrambled by the instability. Bad. The way to stop a Kelvin-Helmholtz instability is to put in a magnetic field that goes along the flow or a viscosity. And I argue, I'm going into detail here, that viscosity is much more likely put in a small viscosity, and you get the smooth pattern here, which has a sharper nose than Cygnus A, but apart from that, it's smooth. And this is the first successful calculation of a smooth boundary backflow. And you can see the arrows get smaller. There's a deceleration as the stuff flows back. And that is because the material in this relativistic flow of cosmic rays is moving up into a pressure gradient. There's a slow negative pressure gradient throughout the cluster, throughout the cavity in this region. So it's being decelerated as it moves back toward the center of the cluster. And this deceleration causes the toroidal field and a BR field also to compress. In other words, as you decelerate, the lines of force get closer and closer together. So the field strength goes up as you go back toward the center. And that's bad. We don't observe this, as I'll show. But the basic idea of the boundary backflow is correct. Here is my calculation that shows the emissivity approximate emissivity of radio emission at distance 35 kpc from the center of the cluster, and its projected image in solid line. And these are observations of Cygnus A. And look at there, the dashed lines are the same in both cases. What they did here was deconvolve the cross-sections emission at each distance from the center of the galaxy and find out what the emissivity needed to be to produce these flat contours. And you can see it's double peaked. Just so that, but the authors of this paper didn't understand what this meant. The double peaked is the backflow. So the radio emission from FR2 radio lobes comes from the boundary backflow. So it's very limb brightened, very limb brightened. And this is similar to the gamma ray emission from the Fermi bubbles that Guo and I recently studied, where the gamma rays come from just the edge of the bubbles. Okay, so my calculation allows for the first time a connection between the observed field in the shock spot and the field observed in the backflow region. And when I look at my calculation, I find that the magnetic field energy here, b squared over 8 pi, as a function of distance perpendicular to the jet at various z values, starting far out and coming back toward the center of the galaxy, those contours are growing. This shows what I mentioned a moment ago, that the magnetic field grows because of this deceleration. And in fact, it grows to be absurdly large. It's at least 20 times bigger than observed in the radio halo from X-ray and radio observations. And not only that, the radio emissivity increases along the decelerating boundary backflow. So whereas the observations of Cygnus A show the radiation that I computed increases, but the emissivity observed in Cygnus A decreases along the backflow, that is, toward the center of the galaxy or the cluster. So the toroidal magnetic field is not a good a model for what's going on in Cygnus A. Now for another insight, which is somewhat unrelated to the radio cavity, is what's going on in the hotspots, so-called hotspots. Well, what I call the shock spot is the hottest place in the cavity, because that's where the jet energy is being deposited. But it's not the hotspot we see. What we see, what radio and X-ray astronomers see, is the hotspots that I pointed out to you, is this place where the wind going in the forward direction smashes up against the cluster gas for the first time. I'm not going to make it to that. And compresses, the B field goes up, B squared goes way up, and so the emissivity for things like radio synchrotron emission and synchrotron self-Compton goes way up. So the hotspots are not the place where the jet is hitting the cluster gas. And yet there, the hottest place is clearly right behind the shock. So I've dropped the use of the term hotspot altogether. I use shock spot and offset or bright spot. Okay, so this offset is, in this case, about 1.5 kpc ahead. Now, there are objects in the sky where you do see the actual shock spot. Here's a jet coming in. This particular hotspot region is 500 kpc from the cluster center, about 10 times further away than in Cygnus A. And you can see what we think is probably X-ray synchrotron emission coming from directly behind the shock. And in front of that is a separate region emitting X-rays in gray due to synchrotron self-Compton. And the radio contours show an arc-shaped region, as similar to my calculations, of radio emission from that compressed region also. If you let my calculation run a little longer, twice as long, the distance between the actual shock spot and the bright spot offset increases, just because the density of the cluster gas goes down as you move out. So the wind coming from the shock material can actually move further forward and push the local gas slightly further away. But what I'm doing is moving the hot spot at a constant velocity. However, in nature, how does nature know to do this? How does nature know to produce this offset? Well, when I analyzed my solutions, I found that the entire distance between the shock spot region and the region behind the bow shock is in subsonic communication. That is, the Mach number is less than 1 all through that region. So these two regions talk to each other hydrodynamically. So the shock knows where to form so that it can produce a momentum balance with the wind flowing this way and the jet coming in this way, and accommodate this offset, create the offset. The offset is created automatically. So what we found is that Kelvin-Helmholtz instabilities must be damped. Yeah, use viscosity, we can talk about that if you want. Radio synchrotron emission occurs only along the boundary backflow, and so it's very strongly limb-brightened. The hotspots are offset emission ahead of the post-shock shock spot. Toroidal fields evolve into lobe fields that are much too large and have the unfortunate characteristic of increasing along the backflow, which doesn't fit with the observations. Now, recently I've done more calculation, and I've actually calculated the detailed energy distribution of the cosmic ray electrons at every point in the radio cavity. This has never been done before, and I'm only using observations from the shock spot to do this. And I'm able to estimate then the radio synchrotron emissivity and flux from anywhere in the radio cavity just by integrating along the line of sight. And the results I get support random small-scale magnetic fields and electron pairs rather than electron-proton dominance in the jet. So there's a generic equation for how a distribution like this varies with energy, position, and time, and it's this one here. And in the case of Cygnus A, the gradients in the density are small. So I'm approximating this divergence term with n times the divergence of u, which gives a very simple mathematical result. So I'm assuming basically a Hubble flow. I'm assuming that a 3D Hubble flow, and the losses here, sigma dot or gamma dot, are due to expansion and radiative losses due to inverse Compton and mostly synchrotron emission. So the solution of this equation, now written in a different way, initially satisfies at time t equals 0 a power law, okay, is this expression. And it consists of two terms, an expansion term and a radiation term. And the trick here is to cast the temperature, the time over the initial time, the age of the cosmic ray particles at some place in the cavity to the time when they were first emitted from the shock spot, to the local energy density of cosmic rays divided by the cosmic ray energy density in the shock spot at the retarded time when those cosmic rays were emitted. So I use the concept for Hubble flow that rho goes as t to the minus 3, EC goes as rho to the 4/3, and you turn that inside out and you get this expression here. So instead of using time, I use the energy density as a guide to this term. Here I use the real physical time, the physical age of the particles that are losing energy mostly by synchrotron emission. Okay, and here this shows in my dynamical calculation how the energy density in the shock spot decreases and how the density of gas decreases as a function of time. And the reason for this is just the variation of the cluster gas. The source function is pretty constant in my shock spot, but when the density is high, when the surrounding density is high, the density in the shock spot and its energy density are high. So it isn't until later times that it can blow away more material and flatten out, like I've shown. Okay, so what happens here is in Cygnus A is not a simple power law, but a double power law. So you just need two of those solutions that I pointed out. And the observations are not at the shock spot. The observations are at the bright spot. This is what everyone thinks is the shock. But the observations are in this case, 1.5 kpc removed from the real place I'm interested in, and that is the post-shock region. So I need to use my model to correct this constant k by some factor of order unity. So the shock spot k is about 1.4 times the bright spot. So I use the observation here of Stowart's. It's a nice paper. And the field he picks is like 220 microgauss. But I cut that down by about 1/3 to 62 microgauss. So it's 62 microgauss is in the shock spot, and that correlates, that field increases when it smashes into the offset region. Now, this may look complicated, but these are vanilla equations that everyone would use to calculate radiosynchrotron emission. If we know the number density of cosmic rays at any time, we can combine these formula and come up with an expression for the emissivity as a function of frequency. And I'm using the local field because of the deceleration. The electrons in the backflow spend most of their time far along the flow, where the field is measured. Okay, skip this. So now I can calculate and compare the emissivity as a function, a radio emissivity as a function of distance from the jet axis at various distances coming in toward the center of the cluster. These are in kpc. And you see for the toroidal field, the field strength and the emissivity are increasing to more than an order of magnitude. So by the time I get up here, I'm way above the observations. Now the observations are shifted in two ways here. The observations are much lower than the toroidal field, but there's also a vertical, horizontal shift. And that's because the shape of my boat-shaped single jet position calculation is different than the rounded shape of Cygnus A. So the distance here, the horizontal shift doesn't bother me. What's of interest is the horizontal shift. You understand? And at each point, say the point I picked was at the peak of these curves, I can plot the number density of electrons as a function of energy and their emissivity as a function of frequency. And the magnetic fields are just, as I said before, much too large. The observed fields are around 20 microgauss. Now what I did was depart from using the induction equation, give up on that, and assume that the field is organized in some subgrid way, in a random way, so that the field itself behaves like rho to the 4/3, like a relativistic, any relativistic fluid would. So let's assume a random field which scales as the local density, but is normalized by values at the shock spot. And now I'm getting results that are much better. I'm getting closer fit to the observations, which are these dashed peaks here from the observations, and these are my calculations. And you see I'm getting a slow decrease, just like in the observations. And the field is constant along the backflow, just as the current observations suggest. So this means that even if you were to use flash and overcome the magnetic monopole problem, you would get the wrong answer. I think the toroidal field is an indication that fields on the scale of 1 kpc of the grid zones or larger get compressed in the way that I was talking about in the deceleration, whereas smaller fields behave in an entirely different way. Fields with smaller scales, like in a turbulent environment, give us results like I've just shown here. So what I did now was, instead of picking 10 to the 46 ergs per second, I picked 2.6 times 10 to the 46 ergs per second and recalculated the model. The reason for this is that with this value, I get exactly the volume that observed, the total volume in Cygnus A, regardless of shape. And I didn't do that in the beginning because I was not slavishly trying to follow the exact observations of Cygnus A. But in fact, this is a more accurate calculation because now it has the right cavity volume. And you can see the fit is even better here, between the level of these peaks and the observed peaks. This implies that the field is really sub-kpc, in my case subgrid level. Now this is the final point I want to make. And it's like a holy grail. People have wondered, when the radio and X-ray astronomers working together furiously, in many papers in the literature have tried to discern whether the cosmic rays are relativistic plasma, electron-proton plasma, or whether it is a pair plasma. And it's a mess. They can't, by observations of the radio cavity are just not good enough, and there are many difficulties here. However, what I did was a different comparison of observation with theory. I compared the energy density observed today in the shock spot. Actually, it's observed at the bright spot, but translated to the shock spot. And the energy density in the shock spot that I calculate to produce the same volume of cavity. And just assuming electrons purely, if I take this distribution then, integrate over the entire distribution, I get, depending on the cutoff, unknown cutoff at low energies, I get values on the order of 2.9, 2.5 times 10 to the minus 8 ergs per cubic centimeter inside of electrons only, radiating electrons only inside the shock spot. And the normalization factor has been corrected from observations of the bright spot to the value in the shock spot for the second calculation that I did, okay? Then I looked at my calculation, that plot I showed you earlier. What is the energy density in my calculation of cosmic rays? EC doesn't tell you anything whether they're protons or electrons. But what is the energy density of cosmic rays that I need in the shock spot today to produce that same volume that we of the entire cavity? And lo and behold, it's exactly the same. So there's really very little room here for relativistic protons. Proton would have 1,800 more, a factor 1,800 times larger here. So there's no way to avoid the conclusion that the shock spot, and therefore the jet, and therefore the cosmic rays inside the radio cavities, is dominated by electron pairs. And this is a very good result, because we think, experts, Blanford and others, think that the way these jets form is basically electromagnetic. So if you have electromagnetic jets, origin, then you tend to form pairs. You don't form a normal relativistic plasma this way. So this is a very gratifying result, and I think this is a better, perhaps the only good calculation of this available that I know of. So these are the more recent results that I just described to you. I'm sorry I went longer, but I'm special.
Indeed.
And I'm being honored at this conference on galaxy formation, not something that I've really worked on really directly. But this is such a fun subject for me. And you wouldn't believe the ramifications of this. I mean, one could take this and run with it and produce a huge number of papers and further insights. Thank you very much.
Thanks very much, Bill. I apologize to you all that I was so interested in all of the afternoon's talks that I let all of them run long. And so we don't have a lot of time for discussion, but let's take a few questions for Bill. Sandy.
Totally ignorant question. Bill, what is an electron pair?
It means electron-positron.
It is.
Yeah, so it's neutral charged. Okay. But the question is, yeah.
And exactly how were those created?
Well, these were created by interactions with the extremely strong electromagnetic fields, with the cosmic ray environment, with the background radiation and other things near the black hole. And then this stuff flowed as a jet out. So the field and the pairs moved out in the jet. And we can't, observations of the jet are ambiguous. We can't tell whether the electrons have proton components or positron components. Yeah.
Tom.
I actually had two bases that asked whether the electron-positron pairs. Since you have all the model parameters, what telescope will you expect to measure that pattern?
Sorry, what telescope?
Pair annihilation. I'm wondering when you expect this pair annihilation
to
actually be seen from a system level.
Velocities are so large here that you wouldn't expect much. Annihilation only occurs when you get to very low temperatures in a pair plasma. And then you produce positronium, which decays and stuff like that. That's not going on here. The particles are independently moving relativistically with respect to each other in the field.
Let me ask the second one. So you called your second feature to distinguish the bright spot and the inner spot that's, if you compare this to a regular sort of 1D model of a supernova remnant, you would have a forward shock and a reverse shock, which also would be separated by contact discontinuity in subsonic region. I was just curious of whether you actually have any differences in this.
I haven't thought about that, but clearly it's very analogous. What you just described is very analogous to what I found. Yeah.
One more question? David.
A naive question. That is, now that you do understand a lot of the physics and what's happening, as a theorist, is it now possible to go back to the best simulations and actually watch this process and maybe get some more detailed
Yes.
topology and stuff? So,
Yes. And Cygnus A only has 200, 200 kiloseconds of Chandra time. I mean, this is something you put on some. I mean, this is an insult. This object ought to be observed deep, so that you can do this deconvolution and find out exactly where the thermal and non-thermal X-rays are coming from. Also, the radio observations need to be done just like those guys did. They deconvolved perpendicular to the jet and found that the emissivity was limb-brightened. They had no idea why. But that ought to be done standard now with all radio observations of these objects, so we can get a better sense of what's going on. Yeah, observers need to just start from the very beginning again.
Is there another object like this that you can study? To sort of
Yeah, there are some others. This is the brightest radio source in the sky, discovered by Rote-Grieber. Or was it Grote-Reber? What a name. Imagine naming your kid Grote. I mean, honestly. Anyway, yeah, back in the 30s it was discovered. Yeah, but there are others that are quite bright that can be studied in detail.
All right, thanks very much to Bill.
Thank you.